Hey everyone, so today we're going to go over linear models and start to do some statistical tests in R. And so first, to start off, here's the agenda. We're going to go over linear models. Then I'll talk about more complex forms of multi-level models. Then I'll run over the assumptions for each of them. And then I'll talk about how to assess models. So first, if maybe you've taken an introduction to stats course before, you probably have heard of all of these different statistical tests you can do. And you might be very confused and it might be hard to keep in mind which all of them are. But I have some good news basically that all of these are really just the same thing. They're all just linear models. And so while we'll have to know some of the key differences between these, and mostly just what a categorical and continuous variable are. The nice thing is that when you're writing these models in R, you'll use the same exact form for all of these. And so we'll just, for basic linear models, it's just the object LM, and then your response variable Y, like I've written down here, distributed by, and then you list your predictors X, in this case, and Z. So X plus Z. Also, you would include data equals your data frame so it knows where these columns come from. So the main thing I just want to mention is that all these are just special cases of just this general this linear model. And so just a linear model in this case, really what it signifies is that your response variable, Y in this case, is some kind of continuous variable that's normally distributed. That's the real key to it. And you can throw in as many categorical or continuous variables or as you like. It's more about the response and the fact that it's just mostly about the response. Okay. And if that didn't really click for you, take some time to think through this table. This table kind of runs through, I can't put my hand down here. This table kind of runs through all those different tests and just kind of shows you how they're all just a linear model and what exactly they're showing. So this is pretty helpful too. Just everything's a linear model. So just to go over some of the basics of what a linear model is. So the idea of when you're doing a linear model is you're trying to partition as much of the variance as you can. So here's an example of just like a linear regression. So we're taking some continuous variable called x1 as one of our predictor or independent variables and trying to explain as much of the y, so a response variable, as possible. And so you do this by taking, say, all these points, and you try to fit a line that minimizes the amount of the spread between those points and that line from like just based off the distance in y. And so there's just special algorithms in R that can solve this for you, and they'll just find that best fit line. And so when you run the LM object, it creates it for you. And then you can get then say some of the coefficients from the model. So the slope, which here, and then also just the intercept in this case. So this is just how a basic linear model works. It gets to be more complicated as you add other factors or predictors to the model. So what we showed before is just this top one here, just a straight line with a y-intercept. Say you added another predictor now, so it's P plus Q. And this time, now we're just essentially just adding another coefficient for beta. So that is what the beta 2 is the other coefficient. And then if you wanted to get more complex, you can actually then allow there to be an interaction between P and Q. And you do this by adding this third coefficient beta 3 here at the end. And I'll explain more in non-mathematical terms what is happening with this next. So imagine you had this data set here with x1 and x2. And so in x1 and x1 is this continuous variable like we had before, but now we have x2, which is this categorical variable with levels. So that's like the um, different categories within that categorical variable. So the level of A, B, C, and D represented by the different colors. And you see here that we just have this big scatter plot with them. And so before, as I was mentioning, right, when we just did that, we had those two, we had our intercept and slope. But then if you added that other variable, it could allow you, if you just added in an additive model, the third beta 2, I believe, would allow you to then get different intercepts for each of those lines. But if you add a interaction term, that extra coefficient, the extra beta 3, sorry, I might have said beta 2. Let me just go back to the table, easier. So in this is like the additive one, right? It's beta 0, beta 1, beta 2. And then our interaction, right, we're adding this third term here. And you can see we have, you're taking in the two factors into account, but then you're scaling them by that coefficient. And so by doing that, it allows you to actually have the slopes vary. And so you have a much, much more complex model. So on the left here, right, if you see the overall slope for this whole thing is negative, so then they're all going to have the same slope. But because the inclusion of that additive term, we're going to get different intercepts for each of the lines. So each of the lines are separated. But you can see, like for the green dots, it doesn't fit that data really well at all. So when you add the increased complexity of the interaction term, now you can see with varying slopes, it fits that green data really well. And I'll talk about in the end how to assess which model of these two to choose and run with, but that's more at the end. And so that's just give you a brief overview of how linear models work. Now I want to kind of dive into multi-level models because that's actually probably what most of you will be doing. I'm not certain a lot of you will be building multi-level models like I'm going to talk about today. But if you're doing any kind of time series where you're taking any spatial or temporal autocorrelation, you'll for sure be building multi-level models. And I'll try to explain why in a example that's doesn't exactly tie into temporal or spatial autocorrelation, but explains the basic principles for why you have to take those into account in those models. So here's a great example of a problem. Imagine you were really interested in measuring some quantity of streams. So I don't know, take like dissolved oxygen levels in streams. And say you wanted to look at 3 different points like across all the streams and say that you expect as you go further down the stream, the dissolved oxygen is going to increase across it. So you went and you're trying to get a pretty good representative sample of like streams across New Mexico. So you went to 3 distinct streams and you measured those 4 points along those streams. And so once you have all that data, then you want to analyze it and figure out what was happening. And so this is like kind of a classic multi-level model, or it comes in many different terms. If you might have heard of hierarchical models, you might have heard of mixed models, mixed effect models. All of these mean the same thing. But essentially, again, this question, like, what is your sample size? So you're looking at 3 different streams, and you sampled 4 points along them. And I think some people just assume, okay, well, maybe it's 4 points because we're looking, or sorry, 12, say 4 and 4 and 4, so maybe 12 points. Maybe that's our sample size. But you have to keep in mind for when we do any of these kind of tests, you need independence among your samples. And so you run into this issue in where if you look at, say, this first stream here, if you're sampling this one X here, and then you're sampling this X here, chances are, because they're all part of the same river, there's probably gonna have whatever is happening at this X is probably gonna greatly influence this X as well. And so these aren't independent samples anymore. Now these are all correlated samples. So whatever happens here, whatever's upstream of even this X is probably influencing this and this. And so essentially, right, you will really only have 3 independent samples, this one stream, and this one stream. because these are all correlated within it. And you might think, oh, this sounds awful. Like, um, does that really limit what you can say? Yes and no. It's more that you just have to build that into account in your model. And you can do that by building these multi-level models. So multi-levels are basically just saying you're acknowledging that there's some kind of nested structure. So all these samples are nested within this site. And once you take into account that, you are building up these kind of correlation covariance matrices that allow you to then actually accurately statistically represent what's going on with them by building a better model. So hopefully that made sense. So, right, you have these what are called intra-class correlations. So as I mentioned, like statistical tests assume independence of observations. You don't have that. Each of those streams or the samples of them are highly correlated. But we can take that into account by building in that structure. And so it's really awesome to build these models because it allows you don't have to say average all the stuff within it. You don't have to kind of pool some of your samples. And so you can then actually really represent, say, like temporal trajectory. Because right, if you're doing a time series, the point where you were before probably greatly influences the next point in that time series. So you have to keep that all in mind. And lots and lots of stuff in the world is built or is in a nested design. Typically in my world of ecology, we do a bunch of block designed experiments. And so those are all set up with individual blocks and we throw those into our models. But you could say there could be site level random effects if you're measuring a bunch of samples within the same site. Yeah, that's the main thing I want to say here. Am I missing anything? So how do you build random effect models? So the tricky thing and what trips a lot of people up is that you have what are called these two factors. So for your predictors, they're either what are considered fixed effects or random effects. And it gets to be super confusing, but generally the way most people think about it is just your fixed effects are if all the possible treatments or levels that you're interested in are present in the factor. And then random effects are just factor that contains like a random sample of the possible levels, treatments, or conditions. And so if that doesn't make much sense to you, it's make more sense once I start showing some examples. But essentially it's, say like in our stream example, we had some idea if those 4 points meant something across streams, like this is like the beginning, the headwaters, this might be like further along in the stream. But the specific streams we chose weren't super significant. We just chose 3 that were pretty representative. So imagine we just pluck 3 from a random distribution of streams in New Mexico. So the streams there, right, it's just a random effect. We don't really care to estimate how the streams differ, but what we really do care about is estimate the lengths across all those streams. So mixed models are just going to contain both of these kind of factors. So if you're doing a normal ANOVA, say like a 2A ANOVA or like some kind of multiple regression, all these will be fixed effects. The other thing to mention is random effects are conditions and are going to be categorical. So all your covariates will have to be fixed effects. So here's some just brief examples. Time series data is well, I guess, sorry, to take that back, like you can, random effects, right, can be your spatial and temporal autocorrelation. So those would be continuous, but we're not going to talk about those today. What we're going to talk about more is like these nested examples. So like the most classic examples are site. So sites are nested within an ecosystem and biome. So imagine you're really interested in studying, say, like how wildfires might affect, say, some streams or something. Or a better example, one of the classic ones they did was there's this area in Kansas, and so they brought in a bunch of bison. And they put all the bison on one side of the whole area and left the other side without bison. And so this created a huge kerfuffle because they're they didn't have any actual replication because they only had the bison on one side and the others on free on the other side. And so because of that, right, because their unit of replication was one of the two sides. And so what they should have done, right, is had a bunch of sites with all the bison and some of those and not the others, etc. So basically sites are going to be nested within ecosystem. Plots within a block is a great example, but think also the streams as well. Okay, so now let's just kind of go over some of the assumptions. So one thing you have to keep in mind whenever building any kind of models like linear or mixed effects or multi-level models, you have to make sure you're satisfying these assumptions, because if you're not satisfying these assumptions, your statistical tests and your results are not valid. And it's not, some of them matter much more than others, but if some of them are violated, you can't take any of your results seriously because the test just doesn't work. So the first one is normality of residuals. So when you fit your model, right, there's going to be some error term of stuff that can't be explained by your predictors or random effects. And so that kind of errors, that kind of leftover, can be modeled, and you want to make sure that it's all normally distributed. And I'll show more in a second what that means. Second, you want to make sure there's homogeneity of variances. So you want to make sure the variances are equal or close equal across all of it. And then you want to check for no multicollinearity. So when you have multiple continuous predictors in your model, you want to make sure that they're not highly correlated, because if they're extremely correlated, you can run into issues where your coefficients in your model can be extremely unstable, and it can be really hard to know what's happening in your model. So normality of residuals, it's really easy to test this in R. You can just build these things called QQ plots, and it just looks at different quantiles and make sure the residuals kind of fit this straight line. I'll show you how to do that in there. So you want to make sure your residuals follow this line as close as possible. You have some deviations, it's not too bad. What often happens is you have ones that kind of diverge off at the ends. These are usually due to having either too fat of tails on your distributions or too skinny of tails. But you want it, as you see in this panel, to kind of fit a normal distribution as well as possible. So that's your first condition. Second one, probably the most important, is homogeneity of variances. It's also referred to as homoscedasticity. And so you want to, this one, you want to make sure the variances across your groups are roughly equal. And this one's much, much more important than the other one. So you want to make sure you solve it or satisfy this. In R, this is done by creating these things called residual versus predicted plots. And so imagine you have some data X and Y, and you fitted this line here. And as you can see in this like plot, right, the residuals down here, they fit it really well. There's not much, they don't diverge well. As you get further up, it fans and fans out. And so this is our issue where you can see the residuals are really expanded here versus here. And so when you create a plot of the predicted versus residuals, you get this fan shape here too, because as the value of your fit, your predicted value increases, then it's growing as well. And so this is not good. You don't want any kind of shape within your residuals. You want this to be kind of like a just dots everywhere, but equal without any kind of shape. Kind of like this. This is what you want to see. No exact shape. The residuals look relatively equal across your predicted data, predicted plot. And sometimes you have other issues where it doesn't fit it well. And so you can get other weird shapes like this. This is also usually a time that usually means maybe you need to, it's maybe not linear data, something to look for, but none of these shapes are good either. You want to figure out what's going on with that. Finally, multicollinearity. So you don't want any of your variables to correlated. So what you can do is either run correlations with each of them. So this is just kind of showing you a plot so you can get an idea of how correlated they are. Or the other thing you can do is run something called variance or a VIF. variance inflation. I'm blanking on what that stands for, VIF. And that will allow you to calculate it too, if you have multicollinearity. And I'll show you that in R. So yeah, so basically the big thing is it won't give you valid results about any individual predictors because they'll become extremely sensitive to new data points. And so you could have, say, predictors switch from like, say, a +2 to like -4 with an addition of a point. So it's incredibly unstable. It makes it hard to know what to believe with the individual predictors. So say we satisfy all those conditions, we built this kind of complex model. We usually start with a complex model and kind of dwindle it down. Now let's try to assess like the best way to, which kind of model should we go for? And we do this by doing kind of, there's multiple approaches. You can either use, say, a likelihood ratio test. And this is where it basically, if you're looking for just like comparing multiple hypotheses, like in a null hypothesis testing kind of framework, this works really well. You build your more complex model, and then after you do that, you can test it with a less complex model, and then you can compare the likelihoods and choose the best one. And the top one will give you a p-value, which can be helpful. The other way to do it is more of a model selection approach, or you can use AICC. So AICC is an information criterion where you're trying to find the most parsimonious model that fits the data as well as possible. And so it discounts for greater complexity, but it allows you to try to fit the best model possible. I'll explain more now. So here's kind of like how the chi-square likelihood ratio test goes. Helpful because it gives you that, but you need to make sure you're using the exact same data for these and any transformations. And also make sure you're using maximum likelihood estimators, which I'll show you how in there. Then for AICC, it's helping you build this kind of trade-off of building a more complex model and one that fits the data as well as possible. So, right, if you add all these parameters in the world, like if you threw in like 100 different parameters, it would partition all the variance extremely well. And then you would have a model that fits, or that gives you like, say, a good likelihood. But right, you're probably overfitting the model and adding all these things and creating something that's super well fit, but isn't really what's happening. And so you want to avoid this kind of overfitting, and AICC can kind of help you determine what's the most parsimonious, like the simplest model that fits the data as well as possible. And so it does this by first calculating like the maximum log likelihood. So you calculate the likelihood. Then there's this thing called a penalty. So it takes how many parameters you're estimating in your model, and then it calculates, it creates a penalty. So the more parameters you include, the bigger the penalty there is. And then this other term at the very end is correcting for a small sample size. So this is helpful because a lot of times you don't have huge sample size for a lot of these experiments. So it's important to include this and run the AICC as opposed to normal AIC. And so when you have these different models, this historically people usually refer to a difference of 2 to help decide which models. And so you want the lowest AIC score if possible. And so typically how people approach it, like the main rule of thumb usually is you want to choose, if you have 2 models that are identical in the number, your AICC score, you want to choose a model that is simpler, it's the one with fewer parameters. And if it's the case that, but if you have a more complex model, let's say above 2, or sorry, below 2 in an AICC score from the other models, then you can probably keep that more complex model. And 2 is just kind of, it's an arbitrary number. You can choose higher numbers if you want. Last thing I just wanted to mention before we jump over to R and I give you some more examples is always try to plot your data before you dive into these stats. Make sure you understand what you're seeing. And so this is one of these classic examples where you plot all this data and you can get the same summary statistics for each of these plots. But obviously what's going on in each of these is very, very different. And you want to make sure before you dive in, you're knowing what you're getting yourself into. So the first plot looks great. That's what you expect to see. Second one, clearly you're not fitting it well. And this probably needs some kind of other added terms to make it parabolic. Third one, right, we have this 1 point here. It's a massive error. And so it's probably, this is just some kind of outlier. It's pulling it off. And then here, this is called influential point. So then you see all these are crowded around here, but this point here is really guiding the trajectory of the line. So this point is influencing it and would have a lot of what's called leverage. Okay, so let's dive into some of the R stats. And so I have a new R window I opened up, and we're going to dive into it. So first, I was just going to walk you through some of the packages I've loaded. So just tidyverse always. Tidyverse is great. Load that up. I'm going to use the Palmer Penguins dataset because it's a nice, easy one to show some of these tools. To build linear mixed models, multi-level models, whatever you want to call it, I use LME4. I think that's the easiest one to use. To do some of the ANOVA, some of the model testing, we'll use CAR and also some variance inflation. And I can't remember what VIF stands for, so I'm going to look it up quickly. Variance inflation factors. Sorry, that's what it stands for. We'll use mu-min to get the AICC scores. And then for kind of post hoc tests, we'll use this package called EM means. That's super helpful for that. Okay. And more on EM means, check out this link. They give you a lot of really cool examples. So this cheat sheet's super helpful. Use that. So let's just create some fun plots in R, using the Palmer Penguin example. So I'm just gonna, let's say that we wanted to compare, see if the body mass of the penguins differed by species. So we're doing like your classic one-way ANOVA. Are the body mass different between the species? So first, let's just plot it and look what the data looks like. So you remember before, we have this data set, Palmer penguins, the species, the bill length, etc., body mass in multiple years. And so for the first one, right, we're just gonna look at these and you see that like Adelie and Chinstrap are relatively equal, but then the Gen 2s are much bigger penguins from them. So that's kind of helpful to know going in. I would probably expect we'll get some kind of significance because Gen 2s were much higher up than these plots, but we'll know until we test it. But one thing you can imagine too is that probably the males and females are different sizes. So then we can actually add color into here to kind of get an idea of if there are differences between the males and females. And so you can see, yes, it looks like the males are bigger than the females for each of the species, but they look, it looks roughly the same. And you can see there's some NAs in there too. So we'll just write some quick code and remove the NAs using the drop NA, because we don't need those right now. And so you can see here's a cleaner data set. And so we can look at how does the body mass differ between males and females and by different species. And since we have a lot of data, we can actually then test to see if there's interactions between the species. So in this case, we can see like, are the males and females, the differences between them more pronounced in certain species than others? Might seem that way because like you see the Gen 2s the males are much bigger than the females relative to you might see in the Chinstrap species. So we can build a model like this using LM. And so I'm going to take our response variable body mass underscore G, distributed by our predictor species times, so we can include interactions, times sex. And then we're going to have data equals penguins because that's our data frame. And then I'm going to include this na.action equals na.omit. So this thing here just says if there's NAs in this data set, remove them. So this will take care of all the issues we had earlier. So let's create this model here. And so now we actually have a linear regression computed. We have like the kind of the terms for each of the coefficients. So that's super cool. It's already done. All the fancy math, it's already calculated. But now let's check our assumptions. So to check your assumptions for a linear model, you just use plot in the name of the model. And so it's then going to ask you to hit return to see them. So first we'll look at the residuals versus, oops, actually skip the first one. This should be QQ plot first. Go back to it and do it, I think. Oh, maybe it's not. I can just hit the arrow back here because I'll bring it back. So first we can see the residuals versus fitted plot. And so this is just looking for heteroskedasticity. You can see that this line here is pretty close to the 0. This kind of shows you there's issues with that. So it looks like we don't have any issues with heteroskedasticity. This is very homoskedastic, pretty even across the board, no fan shape. Second, let's look at the QQ plot to make sure the standardized residuals look good. Fits the line really well. This is actually pretty solid data. So it's very, very normal. The residuals look pretty good. This is just looking for, you don't have to worry too much about these. This is looking for leverage points too. There's nothing driving this. So sometimes you have a point out here and it'll let you know if that point's going to be highly influential. Kind of like where I showed in that last plot in the PowerPoint. So all of this looks great. Not a problem. If you want to quickly run this, you can then, for any of these kind of multiple aggressions, you can use the ANOVA function. I didn't talk about this much in the PowerPoint, but if you do a type 3 regression, it'll actually partition it by each of the components, and you can just get a quick hypothesis test. So if you run this, you can see we have our species and our p-values and sex, and then also our interaction term. So the interaction is denoted by the colon. And so this is all significant. So we have significant interactions. When you have significant interactions, you don't want to interpret, say, the main effects directly from them, because you can't infer that because there might be stuff going on with the interactions. But we can then we can do some post hoc tests pretty easily. To show you just quickly how the other ways would go. So let's say we wanted to build like an AIC model. So if I was doing like an AIC kind of model for this, I would just kind of build multiple ones. Let me just, so I just named the first one mass species M1. But let's then build a simpler model. It's just additive. And then let's also build one that's just sex. And then let's build one of just species. And finally, we'll build one with a null model. And so now I have to clean these up. So this one's additive now, so we remove the interaction term. Now this time we'll get rid of all the species entirely. This one will get rid of sex all entirely. And then the last one will get rid of everything and just replace it with a 1. And then that will then just create a null model. So it's just not predicting anything, just a flat line, which sometimes will fit just as well as your other models because it's just so noisy. So if we just run all of these, the assumptions should all still be pretty good. It's always worth checking just in case. Yeah, these look good. Often it doesn't make a difference, but check all these. Great. Oh, that one actually does not fit well at all. So that one's not normally distributed, but you can see the other stuff in it looks pretty good. Oops. Oh. Anyways, and then we can fit the species one too. Let's clear that out. How's this one look? Not too bad. Okay, it's probably not fitting sex well because it's binary in this model. So it's probably giving you massive errors when it's fitting it. Anyways, so now we can, using from the car package, we can do AICC to do a kind of model selection. And then we'll just list the models. Sex model might be quite wonky. That's okay. It's exciting. Coding. Let's see what happens. And so just running it, so this runs the AICC, it calculates it for each of your models. You can see a name of your model here. You can see a number of degrees of freedom, so it gives you an idea of the complexity, and then your AICC score. So you want the lowest value possible. So looking at these, we can see the top model actually performs the best out of all of these. So even though that this model is the most complex, it performs better than these other models because 4772 is lower than these other models. And it's not even really close. It's way above like 2. So I would definitely go with this top model based off model selection. And we can do the same thing using the likelihood ratio test. So you can just look at ANOVA. Use that. Just this ANOVA. And you can see here too, you get significant p-value, and so that indicates you should keep the more complex model. So if this wasn't significant, then you could switch to this simpler model. And so you can see all these kind of converge to the same story. That'll happen a lot of the time, but definitely not all the time. And especially it can get a little tricky when it's hard to tell which variables to choose. And my advice for which of these approaches to follow, I think try to think through which philosophically speaks to you the most. Some people just have really hate p-values and are very, I don't know how you describe it, ideological about it. So they might refer more of like a AICC or other kind of criterion. There's also Bayesian information criterion as well. I tend to, for something simple like this, I think the first way is probably fine, this way up here. But AICC works well, and this works, and the likelihood ratio test doing this works well too. Anyways, so no matter what, we're keeping the most complex model with the interaction. And now let's try to do some post hoc tests. So let's do some tests to kind of compare some of the levels within it. So you can't, since we have the interaction, let's look at this model here. So this is me just plotting it and grouping by female and male, so you can kind of see how each of these look. So we can use, say, EM means to then take this model and calculate like kind of the pairwise comparisons to see if some of these within, say like within females, how do the species differ? And then within males, how do the males differ? So that's the first kind of test we can do. And so this calculates kind of p-values comparing them. So when you compare just for females of Adeli's versus chin straps, they are significantly different. You can kind of see that here, that chin straps are slightly bigger than Adeli, but then you get more significant p-values for Adeli versus chin 2 and chin strap versus chin 2, which is kind of obvious because it's much higher up than this. Conversely, you can see for males, you can see Adeli and chin strap were not significant. So there wasn't a detectable difference here, but we can see Adeli versus chin 2, yes, and chin strap versus chin 2, yes. And so it's using the Tukey method for this. And so why we had a significant interaction is probably, I would wager it's because Adeli and chin strap were not different. If chin strap was slightly higher, you wouldn't need this kind of interaction term. But because it fits it slightly better, this is the kind of best model it comes out with. And so we can also try to compare like the other way and just see how do males versus females differ within Adeli, chin strap, and chin 2. We can see that across the board, right, that there are significantly different. All of these, you can see across the board, the males are bigger than the females. So there's some quick kind of ways to do post hoc tests. One nice thing is that from EM means, so just try to explain some of this code again. So EM means first you put in your model name, and then this doing pairwise, so it's telling us to do pairwise comparisons. Distributed by tells you then you want to look at species given sex, or you can look at sex given species to look at the two factors. If you only say had species that are significant, you could just leave off sex if there's no interactions or anything. If you run this without the other term, it'll actually tell you an error like, wait a second, results may be misleading due to involvement interactions. So it's also kind of helpful to keep you from making mistakes. And so you can actually run one of these and then actually save it to an object, and it'll make it into, oops. makes it into this EMM list and list, but you can actually then pull out, say, the EM means, and that'll actually allow you to get the confidence intervals. So it computes actually the 95% confidence intervals for it. So if you run kind of this kind of code where you just pull out EM means, convert it to a data frame, then it'll give you, say, the species, this X, it'll give you this estimate for the mean, standard error, but then the lower and upper confidence intervals. So, and then so we can then actually take all this and plot it using the geom error bar for the lower and higher, and create this cool plot. So here, just a 95% confidence interval. And so it shouldn't look too different than like what you saw before, but it's kind of cool. You can see that Adelie and Trinstrat males are not significantly different. Like you can see some of the overlap with those intervals there. So it's a nice way to plot it. It's not as important for normal linear models to do something like this, but when you start building multi-level models, plotting just raw data can be kind of misleading because you're not taking into account any of the random effects. So I usually like to plot some of the model outputs that way. And I find this much easier to read than the kind of means and standard error plots that used to be super common in journals. I still can never really interpret what's happening other than the standard error looks bigger in one versus the other. So now let's do a linear mixed effect or mixed model or multi-level or hierarchical model, whatever you want to call it, using some of the snowpack data. And so I got this off the same place I got the other data. And so here's just like me reading in this thing. And then I'm going to do a bunch of code to clean it up that I won't really dive into because it's not really relevant for this lecture. If you have questions about what I did, please ask me, but we're just gonna pretend all of it works and get a clean data frame just for now, save time. So doing lots of fancy code, but not gonna worry about it. Okay, and so basically we're gonna be left with is a snowpack clean data frame, and I merged some of the metadata and simplified it, and so I can show you kind of quickly what it looks like. And so I just have in this data set, I took, there's all these sites. There's all these like sites across New Mexico, and they've been sampled over time, many, like from like 1938, I think, until 2020. And then I have the elevation of those sites, and then I also have the amount of snowpack terms on February 2nd of each year. And so by doing this, since we expect that some of these sites to differ, we have repeated measurements over, like, say, a temporal time. And I'm just for this simplicity's example, we're assuming, say, that the snowpack from one year doesn't influence the snowpack from the other year. I think that should be fine for this, but if I say you want to look at snowpack from like March through August, or sorry, March through like June of that year, you definitely want to throw in some temporal like autocorrelation terms in your model because you can measure all that in time and take that into account. But since I'm just looking at once a year and I don't think they should be independent from year, that should be fine. But because of the sites, we have repeated measurements at those sites, we're going to actually use the site as a random effect in our model. And then I'm interested also in elevation, see how elevation affects it. So I'm going to build essentially this model of looking at how does year and elevation affect the amount of snowpack over, say, from over almost what 72 years of data. Is that right, or is 82? "82 years today," yeah. So first, just as I say always, let's plot the data and see what happens. It's going to be a lot, and it's not going to be super easy to read, but it gives you some clues on what kind of issues we'll run into later. And you might not be able to plot your data easily like this, but it might be worth a shot if you can. So I just kind of took it, and I use color to kind of represent elevation. And so the elevation is going to be the same across all these sites because we just are using one elevation or one point at these sites. So each of these facets will have just the same color because it'll be the same elevation. And then on the x-axis, we can see all the years they've been sampled. And so you can see the sampling is not equal across all of this. That's okay in a linear effects model. But you can see that like on the top end, or sorry, the lower end in terms of years, a lot of the sites are missing them. But you can also see that we're missing a lot from the high elevation sites. The light blue ones, there's not that many of them relative to darker blue colors. So this kind of would